today's lecture on X.25 and frame relay. In the last couple of lectures, we have discussed the packet switching technique and also discussed various issues related to packet switching such as routing, congestion control, flow control and so on. In this lecture, we shall discuss about two important examples of packet switch networks such as X.25, which is the oldest one, and frame relay. Here is the outline of today's lecture. First, we shall discuss the basic features of X.25, then consider the three layers of X.25, and then we shall consider frame and packet formats of X.25. You will see that it operates in two layers, data link as well as network layer. Then we shall consider the virtual circuits that is being used in X.25 for data communication, and also we shall consider the multiplexing used in X.25. After that, we shall focus our attention to frame relay, first introducing the key features of frame relay, why frame relay instead of X.25. Then we shall consider virtual circuits used in frame relay frame formats, and we shall see that congestion control is very important in the context of frame relay, and we shall discuss how congestion control is used in frame relay. And finally, we shall conclude our lecture by comparing X.25 and frame relay. And on completion of this lecture, the students will be able to understand key features of X.25, explain the frame format of X.25, understand the function of packet layer of X.25. They will also understand the limitations of X.25, and they will be able to explain the key features of frame relay and understand the frame relay frame format and explain how congestion control is performed in frame relay network. So, let us start with X.25. X.25 is a packet switch network developed by ITU back in 1976. Of course, subsequently several versions have come up, several editions by enhancing the features of X.25, but it is one of the oldest one developed in late 70s. And this particular protocol defines how a packet mode terminal can be interfaced to a packet network for data communication. So, here the user machine is termed as DTE, as we already know. So, this is the terminal DTE, data terminal equipment, and packet switching node to which this data terminal equipment is connected is termed as DCE. We are already familiar with these two terms, and as you can see, DCE is part of that X.25 network, and this particular specification explains in detail how DTE working in packet mode can interface with the DCE and can perform packet communication, packet transmission. It has got three layers: physical, frame and packet layer. So, if you compare it with the OSI model, it essentially occupies the three lower layers: the physical, data link and network layer, and the physical layer in X.25 is essentially X.21, and then the frame layer is, it uses a subset of HDLC, which is known as LAPB. We have already mentioned about it, and then the packet layer PLP. These are the three layers. We shall consider the functions of these three layers in details. First, the physical layer, as I mentioned, deals with the physical interface between an attached station and the link that attaches this station to the packet switching node. So, this is the and which, as you know, this interface defines the physical, electrical, functional and procedural specification. We have already discussed about that. And the X.21 is the most commonly used physical layer standard that has been recommended for use with X.21. However, in absence of X.21, other standards like RS-232C can also be used, which is analog in nature. On the other hand, X.25 is a digital interface, but this RS-232C can also be used in place of X.21. Coming to the frame layer, it facilitates reliable transfer of data across the physical link by transmitting the data as a sequence of frames. Uses a subset of HDLC, as I mentioned, known as Link Access Protocol Balanced, LAPB. It is a bit oriented protocol, as we have already discussed in detail the HDLC. Then the third layer, this is responsible for end-to-end connection between two DTs, and functions performed are establishing connection, transferring data, terminating a connection, and it also perform error and flow control, which is important in the context of DTEs. Then with the help of X.25 packet layer, data transmitted in packets over external virtual circuits. So, we have discussed different types of virtual circuits. Here external virtual circuits are used to perform data communication using the X.25 network. So, here it shows the X.25 interface. As you can see, this is the DTE, this is the data terminal equipment, and here is the data communication terminal equipment DCE, which is essentially part of the X.25 network. So, this interface specifies that X.21 physical interface. As I mentioned, we can use RS-232C in place of in absence of X.21. Then LAPB, which is LAPB is used as the logical interface between the link access layer, and which is the essentially work in the data link layer, and it has got multi-channel logical interface which allows several virtual circuits to be established for communication of data in the packet layer, and user process, as you can see, can communicate to remote users by using this interface. So, here it specifies the X.25 interface, the interface between the DT and DC. Let us look at the frame format, X.25 frame format. So, here the user data is used to form a packet in X.25 packet layer by putting a header which you may call layer 3 header. As you can see, the layer 3 header is attached to the user data to form a packet. Then this packet is passed on to the data link layer, and data link layer adds LAPB header and LAPB trailer, and this is what it looks like, the data link layer frame. This data link layer frame, as we have already discussed in the context of HDLC, has this kind of format. It has got flags at the beginning and at the end, and then the address, then the control and information. And as you know, there are three types of frames allowed in HDLC. One is information frame, which is used for communication of user data, then S frame, which is usually empty, not used, and then the U frame. This S frame is not used in the context of X.25. Then U frame, which is used for control, to pass on control information, because it uses in-band signaling. We have discussed about it. In-band signaling is used with the help of these control frames, U frames. And one point you should notice, here it is essentially a point-to-point communication. So, you do not really require many addresses, only two addresses are used, as you can see here 0000, 0001. This is used by the command issued by DT and response to it. That means, command, whenever some command goes from the DT and some response to it is given this address 0000, 0001. On the other hand, when there is a command issued by the DC and response to it given by the DT, then that is given the address 0000, 000011. So, these two addresses are only used in the context of H.25 because it is a point-to-point communication. It is not a point-to-multipoint communication. However, as we shall see, multiplexing can be done in data link layer. We shall consider about it in details. So, here it shows how the how it works in the packet layer. So, here as you can see, a set asynchronous balance mode packet is sent and an acknowledgement comes, unnumbered acknowledgement comes from the other end for setting up the link, and then the data transfer can takes place, information frame can go, here acknowledgement, unnumbered acknowledgement comes, and not only one but several such data can be transferred before it can be disconnected by sending a disconnect frame, and acknowledgement comes in the form of unnumbered acknowledgement from the other side. So, each time this kind of this type of virtual circuit is created by using this protocol. So, you see the virtual circuits are created at the packet layer, and how it can be done I have already explained, and it uses a virtual circuit identifier. It is known as the logical channel number. So, that virtual circuit identifier is used to identify a particular virtual circuit. As you can see from this DTEA, there are several virtual circuits created. One is going to B, another is going to C, another is going to D simultaneously, and this particular link this DT to DC, this link, as you can see, there are 3 virtual circuits. So, through the same physical link you can create several virtual circuits, and which are identified by a virtual circuit number logical channel number or LCN, and several virtual circuits through the same link using in-band signaling can be created. So, this is the fundamental idea of virtual circuit that is being used in packet layer of X.25. Now, there are 2 types of virtual circuits, we already know about it, that is also used in X.25. One is known as PVC or permanent virtual circuit, which is somewhat similar to leased line that is used in telephone network. That means line always exists, there is no need to dial to set up the link. So, it differs from the dial up link. So, always there is a connection whether you send data or not. Similarly, in here also that private virtual circuit, it is fixed similar to lease line established by the it is established by the network provider. So, the network provider is responsible for establishing this link, providing this link, and data transfer occurs with virtual calls, somewhat packet transfers takes place one after the other, and there is no need to have call setup or termination in case of this type of permanent virtual circuits. However, in case of this switched virtual circuits, it is necessary to have there are several, it is necessary to have link for each data transfer, and the sequence of events to be followed are given here. First of all, links are set up between the local DTDC and the remote DTDC. That means, first a link is established between the DC and DT in the local DT and DC, and also between the remote DT and DC. That is the first thing that is being done. Then a virtual circuit is set between the local and remote DTs. So, after these 2 local and remote links are established between the DT and DCs, the virtual circuit is set between the local and remote DTs, then the data transfers are performed between the DTs, then the virtual circuit is released and link is disconnected. So, this is the sequence that has to be followed for each session of data transfer using switched virtual circuit in X.25. Now, let us focus on the different types of packets used in the packet layer. As I mentioned, the packets can be of different types. It can be data packets. Broadly, it can be divided into 2 types: data packets and control packets. Then the control packets, data packets can be essentially used for sending the user data. user data, obviously there is some maximum limit on the size, and in that size, that limit is used to form the data packets. On the other hand, control packets can be used for various purposes. One purpose is, as you know, to perform flow control and congestion control. This flow control and congestion control can be done with the help of packets like RR, which stands for receive request, RNR, which stands for receive not request, and RAG stands for reject packets. So, with the help of these three types of packets, it is possible to perform flow control and error control, not congestion control. I am sorry, it is not congestion control is not used in X.25. Essentially, flow control and error control are performed. Then the other packets are necessary essentially for in-band signaling. As I have mentioned, you have to set up the virtual circuit, perform the data transfer, disconnect the link. All these things can be done with the help of these packets. And as we have as we know, the user data are broken into blocks of some maximum size, and a 24-bit or 32-bit header is appended to each block to form a data packet. Then it uses sliding window protocol with piggybacking for flow control. As I mentioned, it performs flow control, and go back in protocol for error control. So, it performs flow control and error control using sliding window protocol and go back in for error control. We have already discussed about these two approaches, and we shall see how this is being implemented in X.25 network. X.25 also transmits control packets related to establishment, maintenance, and transmission of virtual circuits, as I mentioned, and each control packet includes the virtual circuit number, the packet type, for example, call request, call accepted, call confirm, interrupt, reset, restart, etc. These are the various control packets that can be sent, that can be communicated between the two DTEs, and additional control information specific to a particular type of packet. So, in addition to the this type of packet, some additional information may be specific to that type may be added to the packet. So, here is the packet format of X.25 system. So, here you see the packets are of, here it is divided into two groups. First of all, as I mentioned, it is divided into three different types: packet, data packet, control packet, and RR, RNR, RJ packets. So, three different types, and as you can see here, the data packet comprises either 3 byte header, here it is 3 byte and here it is 4 byte, and that depends on whether we are using 3-bit sequence number or 7-bit sequence number. So, whenever 7-bit sequence number is used, it is necessary to have 4 byte header instead of 3 byte header, and whenever it is on the other hand, whenever 3-bit sequence number is used, that means you can have 3 bits as the sequence number for for giving the sequence number or for acknowledgement in the user data or in control packets. So, here let me explain the different functions of different bits. This Q bit, this most least significant bit is Q bit. This Q bit is actually not used by this layer. It is left to the user to use it properly for some function. On the other hand, this D bit is used as an acknowledgement from the remote DTE. That means, this bit, as we know, that acknowledgement or flow control and error control can be performed between in the data link layer as well as in the packet layer. So, whenever it is in the data link layer, it is essentially node to node for hop by hop basis, On the other hand, when it is end-to-end flow and error control, then it is essentially in the network layer. So that is being specified by D. Whenever it is D, whenever D is equal to 0, then it is essentially between two adjacent nodes or between the local DC and the DT. On the other hand, whenever D is equal to 1, then it is used for end-to-end flow and error control. So this bit designates that. And essentially the 0 1 or 1 0, these are used to designate the differentiate between the frame sizes, whether it uses 3-bit sequence or 7-bit sequence. Then the 12-bit number, which comprises of two parts, group number and channel number, and these two together forms that channel number, that LCN, that logical channel number, and that logical channel number is used to form a number of virtual circuits. Then the PR and PS, these two are used for acknowledgement and flow control. For example, that PS, the sender uses this as the sequence number of the packet. That sequence number can be from say 0 to 7 if it uses 3-bit sequence, or it can be 0 to 127 if it is uses 7-bit sequence number. Although these are the 0 to 6, it has to be the 7, or I mean the number has to be 7, and here it is 127. So it cannot be 128 or 8. So these numbers are used. This number is used as a sequence number, and PR is used essentially for acknowledgement in the piggybacked form. So that means it uses piggybacked acknowledgement in the using that go back acknowledgement using sliding window protocol, and the window size can be 7 or 128 depending on the number of bits used in the PR and PS field. So that's why you will see that PS is not present in this RR, RNR and RJ packets. So here that PR essentially specify when it is a received request packet, it specifies the number the receiver is waiting for or is looking for. That means it is that this specifies the number, or whenever it is RNR, that means that packet has been corrupted, and whenever it is reject, it is using the error control. That packet has to be rejected by using that go back and ARQ technique. So these are the functions. On the other hand, this M bit is used as the whenever you are using a large sequence of packets, that end-to-end acknowledgement can be done either at the end or for each of the packets. So it is usual practice to send an end-to-end acknowledgement after the end of sequence of the packet. That is being specified by M bit. Whenever it is when this bit is equal to 0 1, then essentially it specifies that end of sequence has occurred and end-to-end acknowledgement is sent. On the other hand, whenever it is 0, then you are using the sequence for each of the packets, acknowledgement is being sent. So we have seen the functions of different fields of this packet layer. Now one point I have already mentioned, and I should emphasize, that is the multiplexing that is being used in case of X.25. This is one of the most important services provided by X.25. As we have seen that a DT is allowed to have up to 4095 simultaneous virtual circuits with other DTs over the single DT DC link, as I have already seen with the help of the 12 bits in the packet which I have already shown. These 12 bits, group number and channel number, with the help of these bits the virtual circuits up to 4095 virtual circuits can be created, and each packet contains a 12-bit virtual circuit number expressed as 4-bit logical group number plus an 8-bit logical channel number, as I have mentioned. Then individual virtual circuits could correspond to applications, processes, terminals, etc. So, you can divide as per the application or processes or terminals. Then DT-DC link provides full duplex multiplexing. That means the data communication can be done in both direction, not just in one direction, through the same link by using in-band signaling. So, we have discussed in nutshell the various functions of X.25 and we have seen how it really works. Now, X.25 was developed back in 1976, where the speed of the telephone network was not very high, only 64 kilobits were sent was the standard. 64 kilobits is not a very high number in today's context. Moreover, the links were very error prone. As a result, it was necessary to have elaborate error control and flow control mechanism, which however is not really required in present day context. That ushered in the development of a faster packet switch network known as frame relay, and we shall discuss about it now. And as I mentioned, X.25 cannot satisfy the present day requirements such as higher data rate at lower cost. For example, if you use X.25 network, since it is a point-to-point communications, if 4 stations want to communicate with each other, we have to set up this kind of point-to-point links. So, if there are 5 nodes which wants to communicate with each other, you will require 10 different links. This can be avoided in frame relay network. So, in a frame relay network, as you can see, each station is connected to a each DT is connected to a data communication equipment, and the frame relay network does the remaining thing. So, here it is not point to point communication, as we shall see. Here it works like a switched communication network. The nodes can communicate with each other and it does the switching. So, as a consequence, it is much more efficient. Moreover, the data rate is much higher in the case of frame relay. For example, compared to 64 kilobits per second used in X.25, frame relay uses minimum of 1.544 megabits per second. Of course, nowadays higher data rates can also be used, but that was the minimum value with which it started. So, speed is significantly higher. Another important point is the X.25 does not support bursty nature of data. It establishes a point-to-point communication, and the data flow has to be streamed or continuous. But unfortunately, in the present day context, it is necessary to have bursty nature of data, because the computer communication uses bursty nature of data. For example, this is the stream data flow, this is the bursty nature of data flow, and the frame relay has been designed to support this bursty nature of data. So, the data can be sent in burst, as you can see. So, within some time, say 8 maybe millisecond, the data is coming in say 3 bursts compared to stream data that is used in X.25. So, here frame relay supports this by buffering the data, and as long as we shall see, the total size, total value of data does not exceed some limit, the packet should be delivered without error. Third important factor is, as I mentioned, in the era of X.25, network was not reliable. The links were error prone, slow. As a consequence, it was necessary to perform flow control and error control, not only between end to end, but between each link, as you can see here. So, here as you can see that the data is going from station A to node 1, and then acknowledgement comes, which are used for flow control and error control. Then if it is correct, then the data goes to the next hop, and again acknowledgement is sent from that particular side. Similarly, from the node 2 to node 3 data goes and acknowledgement comes, from node 3 to node 2 to perform flow control and error control, then node 3 to station B data goes and acknowledgement comes. The story does not end there. As we have seen, there should be end-to-end flow and error control that is being performed by sending acknowledgement from the DTE of the other side, and again the same is repeated between each hop as you can see, and acknowledgement goes from between each hop. Then the acknowledgement frame goes from node 2 to node 1, again acknowledgement of that comes from node 1 to node 2, and finally the acknowledgement reaches the DTE. So here it completes the end-to-end flow and error control. So you see, to send a single packet, how many packets have been transferred? It increases the load in the network, although it makes it very reliable, but increases the load significantly. So in the era of X.25, this was necessary because the links were not very reliable. However, in the context of frame relay, this is not necessary. So what was done? The flow and error control was completely removed, not only in the data link layer but also in the frame layer. So as you can see, the traffic is significantly reduced here. So data goes from station A to node 1, and again data goes from node 1 to node 2, and data goes from node 2 to node 3, and again finally it is delivered to station B. So if any flow and error control is necessary, that has to be supported by upper layers. Frame relay does not support it because it is not necessary. The links are much more reliable, and flow and error control may not be required, and also the speed is high. But as we shall see, it will be necessary to perform congestion control because of higher speed that we shall discuss later. And in frame relay also, the virtual circuit is identified by a number called data link connection number. So here also it is based on virtual circuit creation, and again there are two types of virtual circuits. As you can see, the permanent virtual circuit and the DLCIs, the data link connection identifiers, are permanent and assigned by the network provider. So the network provider provides these DLCIs, and as you can see, there is a permanent virtual circuit created from this station A to station B, or DTE A to DTE B, and this particular link from A to node 1, the DLCI is 75, and between this link the DLCI is 85. So these numbers will be different for different links, and we shall see how this changes later. On the other hand, whenever the switched virtual circuits are created, the DLCIs are temporary. The data link connection identifiers are temporary and assigned by the frame relay. That means the network does the assignment during the connection phase. As you can see, for communication from A to B, these two DTs, the DLCI here is 75, here from 1 to 2 it is 48, from 2 to 3 it is 65, from 3 to 5 it is 98, and from 5 to B is 85. And this is being set up again in a dynamic manner. As you can see, a setup phase is involved for setting up the virtual circuit, and connection is established. After that, data transfer is performed, several packets can be communicated, and finally the link is released, as it is done in case of X.25. So this part is somewhat similar to X.25. Now let us see how the switching takes place within the network. So here each node maintains some kind of table somewhat similar to you may call it routing table. As you have seen, in case of fixed routing, some routing table are stored in each node. So, somewhat similar is done in this case also. So, here you see this node 2, this node or switch, whatever you call it, frame relay switch, this is shown in expanded form, and here you see the table that is being stored. That means from interface, it has got 3 interfaces coming from 1 going to another is 1, 2 and 3. This is the node or switch 2. So, interface 1, this is the incoming. So, when it goes from 1 to 2, the DLCI is 48 and the outgoing DLCI is 65, and whenever it is going to 3, the DLCI is different, 62, and the interface that is goes is 3 and DLCI is 98. And when it comes from the other direction, that means comes from 2 to 1, when it goes in the reverse direction, as you can see, the DLCI numbers are different. That is how the full duplex communication can be done. So, here it is 75 and it is 85. Similarly, from 2 to 3, the 82 and 92, from 3 to 1, it is 52 and 76. These are the DLCI numbers. From 3 to 2 is 42 and 96. So, you see the DLCI numbers are used, how the DLCI numbers are used to do the switching, and using this particular table, the switching is done in case of this virtual circuit switching. So, within the network, each node performs this kind of switching. The frame relay operates in 2 layers compared to 3 layers used in X.25. So, you can see here, this is the frame relay. It has got 2 layers, physical and data link, and the upper layers are provided by others, can be maybe by IP protocol, which we shall discuss later. On the other hand, the X.25 also supports the network layer. It has got 3 layers, as you have already discussed. So, with the help of these 2 layers, the communication is performed. And the frame format used in frame relay is shown here. It has got flag at both ends, then the address, control, information and frame chef sequence. So, here the DLCI, as I said, comprises of 10 bits. So, DLCI comprises of 10 bits. So, you can have up to 1K DLCI numbers, and then you have got another bit which says whether it is a command or response. This bit specifies whether the particular frame corresponds to a command or a response. Then this EA stands for extended address. It is not necessary that the DLCI number has to be restricted to 10 bit. It can be it can have more number of bits. In that case, that this EA bit is used. It is set to 1 whenever it has got larger address. Then FECN, BECN and DE, these are used in the context of congestion control. So, although a frame relay does not perform flow control and error control, it performs elaborate congestion control, as we shall see, and how it is done I shall consider little later. So, we see that how it is being done. The congestion control is performed is explained here. Because of higher data rate and no use of flow control, frame relay network is prone to congestion. As we know that basic reason for congestion is bursty nature of data, and the frame relay has been designed to support bursty nature of data. Link speed is high. These two parameters has made it vulnerable to congestion, and as a result it is necessary to have congestion control mechanism developed for frame relay, and it is done in this manner. So, it uses 2 bits for congestion control. One is backward explicit congestion notification BCN bit, another is forward explicit congestion notification FECN, and also another bit is used. It uses that another bit, that is your DE, discuss eligibility bit, which is used for packet discarding. That means that black, and whenever other things does not work, this discarding is performed. Let us see how it is being done. Suppose this bit, that backward BCEN, stands for backward explicit congestion notification. Let us see how it really works. So, packet is going from the sender in this direction, and it has been found that this part, that beyond 3 in this direction, there is congestion. So, this particular switch identifies by some means. How it is identified, I shall explain in details. This identifies whether congestion has taken place in the forward direction. So, each switch or node does that. So, whenever it identifies that congestion has occurred, then it sends one explicit packet BCN to the source. So, it goes towards the source, and the sender in that case takes suitable measure, so that that means it reduces the traffic, reduces the rate of rate of packets that is being introduced to the network. It reduces that to come out of congestion. This is the BCN bit, use of BCN bit for controlling the congestion. Then comes the FECN bit. So, here you see there is this forward explicit congestion notification. This bit is used to inform the receiver. So, whenever there is a congestion in this part of the network, then this bit is set, and this receiver is informed about whenever this is the direction of congestion in both cases, as you can see. Then the receiver is alerted about the congestion. Now, it is up to the receiver to inform the sender by sending a packet that it is necessary to perform flow control, so that it can come out of congestion. So, by using these two bits, BCN and FECN, you have got 4 possibilities. When these 2 bits are 0 0, that means there is no congestion in either direction. So, and then whenever it is 0 0 1 or 1 0, there is congestion only in one direction. On the other hand, whenever these 2 bits are 1 1, there is congestion in both directions. So, by using these 2 bits, the congestion control can be done. However, whenever this does not work, then this discard eligibility bit is used. This DE bit is used. How it is used? Whenever it is this bit is used to give the priority. That means, whenever it is set to 0, I mean it is set to 0 for some packets and it is set to 1 for some packets. That means, whenever it is using this particular bit, whenever it is set to 1, that means they have the lower priority. That means, these packets can be discarded. So, it essentially sets a priority in the packet. In case of congestion, if packet has to be discarded, based on this bit, packets are discarded in the by the switches. And as we already know, this packet discarding is a very important mechanism that is used for congestion control, particularly when you have to come out of congestion. Now, you may be asking, how do you find out that congestion has taken place, or when to send FECN or BCN bits by a packet? It is for that purpose it is necessary to perform traffic control measurements. So, it is each switch performs some kind of measurement on the network, and based on that it will decide when to send FECN or BECN. And for that purpose, 4 attributes are used. First one is known as access rate. It is decided by the bandwidth of the channel. That means the maximum rate of introduction of packet. So, for example, if the T1 line is used, then the maximum rate is 1.544 megabits per second. That means if a particular node sends a packet at a rate faster than this, then we can say that access rate has been violated. Second parameter is committed bus size BC, the maximum number of bits in a predetermined period. That it does not say that you have to send at this rate. It may be necessary, for example, in 5 millisecond or maybe 5 second, how many bytes can be introduced by a particular source node. That is specified by this committed burst size. So, maybe that this is the duration. Within this duration, it can be introduced in the form of bytes, in the form of bursts. And as long as the total size does not exceeds this committed burst size, it is guaranteed that the packets will be delivered without error. Then the third parameter that is being used is committed information rate. It defines the average number of bits per second. Average number of bits per second, that means it performs the averaging and finds out whether the average number of bits, that is essentially related to the access rate, and this parameter is also specified by the in the beginning, and this average number of bits per second, if it is exceeded, if it is not exceeded, then it is guaranteed that the packets will be delivered without error. On the other hand, if it is exceeded, then the switch will inform the sender that the committed information rate has been exceeded. Then it is the another parameter is excess bus size. This is the maximum number of bits in excess of the BC. Already committed bus size is there. The network allows in addition to B some more before it decides to send FECN or BECN. That means in addition on top of the BECN, suppose this is the limit of the BECN. So, this is the BE. So, this is the BC and this is the BE. So, this much of excess is allowed by the frame relay network, but this is a loose bound on the size. Usually the committed bus size is more important than the excess bus size, but in any case the bus size should not exceed this excess bus size. So, we have discussed how the traffic control is performed and it is used to decide when to send the congestion control, particularly by sending FECN and BECN. Now, frame relay has been designed to not only support or send frame relay packets, it can also send packets coming from other networks, for example, X.25, ATM or PPP, point to point. So, for that purpose is to special functionalities known as FRAD, frame relay assembler disassembler, because the frames of other types of standards or networks like X.25 and ATM or PPP may not be same as that of frame relay. So, what the FRAD function does, it disassembles the packets, sends through the frame relay network. This is your frame relay network. Then at the other end, it does the it performs the assembly. So, assembly and disassembly both are performed by at two ends, and so that you can send packets coming from other protocols, and and that can be carried using the frame relay frames. So, I think this has been repeated. So, frame relay assembler disassembler, its function is it assembles and disassembles frames coming from other protocols, and that can be carried by frame relay frames. So, this functionality is provided and so that it can be made compatible with X.25, ATM and other packet switch networks. Now, before I conclude today's lecture, it is time to compare the X.25 and frame relay packet switch networks, their functionalities. So, we shall compare these features. First one is connection establishment. As we know, in X.25 connection establishment is done by network layer. On the other hand, it is not done by the frame relay. It is done by upper layers. Then the flow and error control is performed in X.25 both at data link as well as network layer, hop by hop and end to end. On the other hand, frame relay does not perform any flow and error control. And as we know, for X.25 the data rate is fixed. On the other hand, frame relay support bursty nature of data. The multiplexing performed by X.25 is in the network layer. On the other hand, frame relay performs the multiplexing in the data link layer. As we have seen, it is done by using the DLCI, and here it is done by logical channel number. Then the congestion control is not necessary in X.25 because of elaborate use of flow control and error control. Congestion control is not necessary in X.25, whereas it is necessary in frame relay. So, it compares these two packet switch networks that we have discussed today. Now, it is time to give you the review questions. First question is, in what layer X.25 operates? Second question is, what are the key functions of X.25 protocol? Third question is, what limitations of X.25 is overcome in frame relay protocol? Rather, what limitations are overcome in frame relay protocol? Then distinguish between permanent virtual and switched virtual connections used in frame relay protocol. Finally, fifth question is, how congestion control is performed in frame relay network? Now, it is time to give you the answers to the questions of lecture number 22. First question was, what is congestion? Why congestion occurs? Answer is, when the offered load crosses certain limit, then there is a sharp fall in the throughput and increase in delay. This phenomenon is known as congestion. We have already seen it is because of sudden increase in the load the congestion arises. And in that situation, as we know, whenever the link utilization exceeds beyond 80%, that is used as a rule of thumb for identifying congestion. And congestion may occur due to sudden increase in traffic in the network. It may also arise because of slow processors and slow bandwidth links, as we have already discussed in the last lecture. Second question was, what are the two basic mechanisms of congestion control? As we know, there are two basic mechanisms of congestion control. One is preventive, based on open loop techniques such as that leaky bucket and leaky bucket algorithm or token bucket algorithm, where precautions are taken so that congestion cannot occur in the first place. On the other hand, another approach is based on recovery from the congestion by using closed loop congestion control techniques when congestion has already taken place. We have discussed various techniques such as choke packet and so on. Third question was, how congestion control is performed by leaky bucket algorithm? Answer is, in leaky bucket algorithm, a buffering mechanism is introduced between the host computer and the network in order to regulate the flow of traffic. Bursty traffic are generated by the host computer and introduced in the network by leaky bucket mechanism in the following manner. Packets are introduced in the network in one per tick. In case of buffer overflow, packets are discarded, as we have seen, as we have discussed in detail in the last lecture. Fourth question was, in what way token bucket algorithm is superior to leaky bucket algorithm? The leaky bucket algorithm controls the rate at which the packets are introduced in the network. but it is very conservative in nature. Some flexibility is introduced in token bucket algorithm. In token bucket algorithm, tokens are generated at each tick up to certain limit, obviously based on the size of the counter. For an incoming packet to be transmitted, it must capture a token and transmission takes place at the same rate. Hence, some of the BASTI packets are transmitted at the same rate if tokens are available, and thus introduces some amount of flexibility in the system. This also improves performance. Last question is, what is joke packet? How is it used for congestion control? As we know, joke packet scheme is a closed loop mechanism where each link is monitored to examine how much utilization is taking place. If the utilization goes beyond a certain threshold limit, the link goes to a warning state, and a special packet called choke packet is sent to the source. On receiving the choke packet, the source reduces the traffic in order to overcome congestion. So with this, we come to the end of today's lecture. In the next lecture, we shall discuss about another packet switch network, that is ATM. Thank you.